All right. Hello, everybody. So let's see. Today is Sunday, but I'm recording this one day in advance of our actual lecture time. So asynchronous lecture today. Actually, it's really going to take the form of just a really quick video to kind of wrap things up. So the good news is we are pretty much done learning new things. We're done learning new things, which is great. So what I wanted to do really quickly is first I'm going to talk a little bit about the final exam, and then I'm going to give you guys a little bit of a sort of a bigger picture idea of what we really did in this class. And then then we're going to do a little bit of U-Substitution practice, because that's one place that I kind of wanted to target, because it seems students have been struggling with that a little bit. So first and foremost, let's talk about the final exam. The day of the final exam is December 9th, 2020, and the exam will, like all the other exams, go from 9 a.m. to 9 p.m. Okay, so I will post the exam onto the Blackboard at 9 a.m. You'll download it like you usually do, and then you'll submit as usual a single PDF file to Blackboard. There will be a review for the final exam. And since we're supposed to do this asynchronously, here's how it's gonna work. It's gonna take place on 11, or I'm gonna post the video on 11/30/2020. And what I need you guys to do is email my email address at thamari@email.sc.edu your questions. So basically anything that you want to be included in the review video, you can go ahead and email me, and what I will try to do is answer every single question that I get via email. So if you guys send me practice problems, I'll do practice problems. If you send me an email saying I'm really confused about U-substitution, I just don't understand it at all, then I'll talk more about some theory. So please do send me an email with your list of things that you would like to see in that video, and I'll try to include everything. If the video has to be 2 hours, then let it be so. Okay, so that's the final exam and the review. Okay, so here's what I want to talk about now. I want to talk about sort of a big picture, because when we've been doing this class, we've been very focused in on the details of differentiating things and integrating things and the process, that I feel like we could use a second to take a step back and consider what we are really doing. So here's the question that I want to answer. What did we learn in this class? Okay, and so we learned calculus, right? And what is calculus? Well, it's really going to sort of boil down to the study of continuous change. And we studied this from kind of two angles. We had differentiation, which was a way of understanding how are functions changing. And then we had integration, which was considering the continuous change of the quantity, which was the area under the curve. So these problems have to do with accumulation. So we have sort of these three tiers here. So we can have some capital F of x, some little f of x, and maybe the derivative of that function, little f of x. And calculus is really about how do these functions play with one another. Okay, how do they play with one another? And in particular, if we know something about one of these functions, what can we say about the other ones? Okay, so these are derivatives to get down here. Okay, so f of x is going to tell us, this function is going to tell us about accumulation of the area under f of x. So if we have some function here, which is f of x, then f of x tells us, if we go to here, this value b, then f of b is going to represent the accumulated area here under this curve, f of b. And the derivative, conversely, is going to tell us the rate of change of f of x at some given point. So the way that manifests is we take a look at this point here and we draw this tangent line. It's been a while since we did that. But if we look at this and consider how is our function changing at this point, then this is going to tell us what is going on here. Okay, so this is about as succinctly as I can put it. Okay, so for differentiation, we learned all sorts of different rules, like the quotient rule, chain rule, product rule, and this was all in the service of just computing these derivatives. Okay, so what we're really interested in is how is this function changing? And likewise, with integration, we learned many rules. We learned some rules for taking basic antiderivatives. We learned some U-substitution techniques for doing integrals, and this is all in the service of understanding the accumulation of area under the curve. Okay. All right, so this is kind of the big picture of what we did in this class. So what I want to do now is go and do a little bit of U-substitution practice, and we'll do a couple problems there and then we'll wrap up. So let's get into the right one here. Okay, so really quickly let me remind you how we do U-substitution. Okay, so we should use U-substitution when we see some kind of integral problem which is either too complicated for us to take the integral of using standard techniques, or it looks like the result of chain rule differentiation. Okay, so let me take a step further back actually and remind you guys the sorts of things which we know how to take the integral of. We learned integration rules for, where is it? Here it is. We learned integration rules for these classes of functions and combinations thereof. So for example, we could do the integral of, say, e to the 6x minus x squared plus 1 over x dx. This is about the extent of the functions that we can find antiderivatives for without using U-substitution. So we should use U-substitution whenever we see things which are beyond the scope of something like this. So this is fine. And if we were to give something more complicated, like, I don't know, why don't we do like 1 over 6x minus 3 cubed times, now we'll just do that, 1 over 6x minus 3 cubed dx. So this is a situation where I really can't use any of these standard techniques to find the antiderivative of this. So this is when it's appropriate to use U-substitution, okay? So let's have an example. Take a look at this problem here, part B. So we have some integration going on here. And we see a couple things being multiplied together. The first thing we see is 8x plus 1, and that's being multiplied by some polynomial 4x squared plus x. And the cue here for me to think that U-substitution might be a good idea is this power 9 here is very large, okay? So seeing that power 9 there, I'm thinking I really don't want to have to FOIL this thing out 9 times. So that's my cue to use U-substitution. So for this particular example, we're going to choose u to be the inside function here, 4x squared plus x. And then we know that we get du by just taking the derivative of that thing and then writing dx. So we get 8x plus 1 dx. Okay? So in this situation, we want to take a look at our integrand. We know we have replaced 4x squared plus x by u. And now I need to consider what are my leftovers. In our case, our leftovers are 8x plus 1 dx. And fortunately for us, that's exactly what we have in our integration here. So all I'm going to do here is just replace the components of the integrand by their representation in terms of u. So I'm going to write an equal sign. I replace what's in red here by u. Those colors don't play nicely. By u, and I get u to the power 9. And now all that's left to do is take care of my leftovers. Okay, my leftovers being 8x plus 1 dx. Well, that's exactly what du is, so I'm just going to write du. And now I can use my standard techniques, okay? U-substitution is nothing special. It's just turning this integral into something which we know how to do. Okay, we take something we don't know how to do and we turn it into something that we do know how to do. So if I want to take the integral of u to the 9, I know I should use the power rule, raise the power by 1 and divide by the new power. And what I should do now is switch back to x, okay? Anytime I do U-substitution with an indefinite integral, I should always switch my function back to x at the end. So I'm just going to write 4x squared plus x to the power 10 divided by 10. And we should add our constant here. So, result of indefinite integration, we get to a family of functions. Okay, so next up I want to talk about this problem. And it seems that some people have a little bit of trouble with problems like this where it's not quite so clear what we should choose u to be exactly. Okay, we have kind of a lot going on here, and none of this really looks like, you know, the derivative of anything else. Okay, but the game that we're gonna play is sort of really just trial and error. Okay, so I'll do a couple options. We could try u equals, I don't know, why don't we try the denominator, square root x. Or we could try u equals, let's see, let me write this over on the other side. We could also try u equals square root x plus 1, the numerator. In this case, I think that's pretty much all we could do. Okay, so immediately I can go ahead and rewrite this integral as, I don't even need to find u here, du here, I can just go ahead and rewrite this. I have the same thing in the numerator and the denominator. This looks like u plus 1 divided by u. And that's going to be equal to, well, u over u plus 1 over u. No, I can't do this, can I? Sorry, I do need to find du here. So let's try it. Du is going to be equal to, this is x to the power 1/2, and then we're going to wind up with du should be 1/2 x to the negative 1/2, or 1 over 2 times the square root of x. So let's try replacing the numerator by u and replacing the denominator by some constant being multiplied by our du here. Okay, so we'll have integral, we'll replace the numerator by u plus 1. And now what's left over is just square root of x dx. So what I want to do is take my du equation and solve one side to look like my leftovers. So I want the right-hand side to look like 1 over the square root of x dx, so I should multiply both sides by 2. So if I do that, I'll get 2 du equals 1 over the square root of x dx. Alright, so we get u plus 1 being multiplied by 2 du. So we can go ahead and distribute out that 2. We'll get the integral of 2u plus 2 du. Anti-differentiate, get u squared plus 2u plus c. So in this case, choosing u to be the square root of x worked out. Another trick we can do is a lot of the times we can just choose u to be the entire numerator or entire denominator if it includes the addition or subtraction of a constant, because we know that when we're going to take the derivative of that thing,